Hi and welcome to video 2 on this series on the normal distribution, Unit 4, Topic 4 of Math Methods. And we're going to talk about z-scores versus raw scores in this video, or also known as z-scores and x-scores. So let's talk a bit about z-scores again first, the standard normal distribution. And the standard normal distribution, of course, has a mu value of 0 and a sigma value of 1. So that's a mean of 0 and a standard deviation of 1. And therefore, it represents how many standard deviations above or below the mean you are. So if we had a z-score of 1.6, this would be implying that this thing, person, object, this data point is 1.6 standard deviations above the mean mu. Z-scores are exact translations on that. So we can explore 1.6 standard deviations above the mean for a normal raw score, for a result in an exam, or for your height compared to the average. But for Z-scores, that 1.6 literally means how far above or below the mean you are in terms of standard deviations. So they're called Z-scores, and they're for the standard normal distribution, where we have 0 and 1. Now this is our normal distribution notation. Approximately equal to, so we're saying Z can be represented by a normal distribution n with a mean mu of 0 and sigma of 1, and I'm sorry, that should say sigma squared, sigma of 1, and this should indeed say a couple of things here, should say 4. So if we're dealing with actual data, we say x-scores, x is approximately equal to or can be represented by a normal distribution with a mean mu of 1 and a sigma squared, which is the variance, of 4, which of course implies that sigma is equal to 2. Now, it's usually sigma squared. Some people represent sigma in that spot there, and for that reason you'll probably not see it actually pop up that often, but that is a way it can be written mathematically. Now I have another question for you, of course. What's blue and not very heavy? Light blue. I cracked myself up. Anyway, moving on to talk about z-scores and raw scores contextually. So here's a bit of a context that I want to chat through to try and introduce it a bit better. Imagine that in a statewide exam, 10 of our students received the following results. Now, I'm not giving a lot of details here about the exam. We don't know whether these percentages, there might be scores out of, the upper score is 77, so maybe scores out of 80, maybe scores out of 77, maybe scores out of 200, who knows. But 10 students get the following result. We're assuming that because it's a statewide exam, it's a really large data set and therefore it can be represented by a normal distribution. Exams are often good examples of things that can be represented by normal distributions. On a rough scale, I've done a bit of a dot plot there. You can see where the results sit. They're not clustered, they're spread out, but it's a small set of data, so we kind of expect that could happen. Comparatively though, I've got 3 possible situations, and I've drawn them up in this graph, so I'm going to just zoom in a little bit here. Oops, sorry, that's gone out there. Comparatively, the orange option has a mean of 50 and a standard deviation of 20. That's a really spread out set of data. Now, if that was the case, then for our school, you can see that 3 of our results would be below average, but 7 above average. And this guy here, 77, is at least 1 standard deviation. That's 1 standard deviation finishing at 70, 1 standard deviation and a bit more above average. That's a good result. If, on the other hand, the mean was 70 and the standard deviation was 5, then we'd have this purple set. Now, the purple set would indicate that 8 of our students were below average, which is bad. But notice here, this 77 is still 1 whole standard deviation and a bit more above 70. It's still a very good result. But in this case, the 42, it is a significant number of standard deviations below. We'll get to this later on. That's almost impossible. That's almost 6 standard deviations below, which is really, really unlikely. But we'll talk about that later. So that's probably not true, number 2. But hopefully you can see how far away it is comparatively, because the purple is suggesting that this normal distribution is not spread out that wide. And therefore, when we get down to the purple normal distribution down here, it's going to be really close. The probability of being there is going to be so low. And then, of course, we've also got this light blue one, which is kind of our center ground one. A mean of 60, a standard deviation of 10, 5 of our students above, 5 below. We're about on average. You can see here, though, that the 77 is almost 2 standard deviations above the mean of 60, and the 42 is almost 2 standard deviations below the mean. So the light blue seems to be the most likely situation because it nicely represents our data. So let's consider option 3 and talk about it in a bit more detail. In option 3, forget about our scores for a moment, but in option 3, a score of 60 is 0 standard deviations away from the mean. Now, if we were in class, I would be getting you to answer these parts, so maybe pause the video and see if you can answer these parts right now. But a score of 60 is 0 standard deviations away from the mean, because the mean is 60. And if x equals 60, then z is equal to 0. I got ahead of myself there. The z score represents how many standard deviations above or below the mean are. And z of 0 means you're on the mean. A score of 50 is 1 standard deviation below the mean. So we represent that as a negative 1. It's 10 below 60. So if x was 50, the z score would be negative 1. 70 is 1 standard deviation above the mean, so it's just 1. So if x was 70, z would be 1. And now we're on to the score of 38, which is actually a pretty tough one. So I'll do this one, and then we'll talk about why in a moment. So 38 is actually 2.2 standard deviations below the mean, because the mean is 60, and therefore the z score is negative 2.2. And the question is, how did we do the last one? And the answer to that question is that I'm looking for a z-score, and as I've said a few times, the z-score represents the number of standard deviations above or below the mean. And therefore, in this case, with a mean of 60, I'll go back to my diagram, a mean of 60, if I drop 1 standard deviation I get to 50, 2 standard deviations I get to 40, I have to drop another 2, which is 2 with a standard deviation of 10, that's 2/10, I have to drop another 0.2. So that's 2 whole standard deviations and an additional 0.2 or 2/10, and that is 2.2 standard deviations away from the mean. How I did it algebraically is right here, and this will be really important. I took my raw score, I subtracted the mean from it, so that is 38 minus 60, and then I divided by the standard deviation to work out the number of standard deviations that fit into that number. 38 minus 60 is negative 22, divided by 10, and z is now equal to negative 2.2. And that leads to this, an important pair of rules. Converting z-scores to x-scores or x-scores to z-scores comes about by doing this. Now we're a little bit ahead of ourselves, but I felt this is important to know for exercise 17A for some of the other stuff we're about to talk about. So later on this will pay dividends because we'll get to converting z and x scores a little bit later in chapter 17. So z is equal to x minus mu over sigma, and x is equal to z times sigma plus mu. Rearrange this first one, you'll get the second one. Try it out if you want to. So let's talk about transforming the standard normal distribution. So we know already, and this is where it's going to pay off a little bit, we know already that if mu equals 0 and sigma equals 1, this is the standard normal distribution. This is a z-score situation. So we get f of z equals this thing here. I've just swapped out the x for z because we're talking about a z-score situation. And we also know that x is approximately equal to n a minus b squared. So here I've done a bit of a diagram. I need to talk about these. I'm going to reference the colours, and so you know that what I'm referencing. This colour here, that's purple. This colour here is pink. So just keep that in mind. I've set my scale up as the probability of z and x. They're interchangeable in this case, and z and x as well on the horizontal state. So first of all, from the black graph, which is our z score, our standard normal, the purple graph is a shift of A. Now, I've not really stated whether A is positive or negative, so let's assume it's positive. That's what I've drawn. you're shifting A. The second graph, the second graph is also an orange dilation of 1 on B. It's actually, you're spreading it out by a factor of B, which actually ends up being times by 1 on B. And this plus A ends up being minus A. So if you go right back to Year 11 transformations of functions, you might remember that when we do things inside the function, so that was when we did things horizontally, kind of worked opposite to what we expected. If you move to the right, we actually subtract A. If you spread a curve out, you actually multiply by 1 on B. And in particular, go back and look at your periodic functions. You see this in real life, like this is where it happens. The other thing that happens though is we squash the curve. So this is the pink one here, and that squash, that's on the outside. So that's a vertical transformation, it's a vertical dilation. So it happens exactly as we expect. Because we're squashing by a factor of B, it means we multiply by 1 on B. So this actually means that our standard normal distribution, which has a function f of z equals 1 on root 2 pi e to the negative half z squared, my 2's don't have strokes to them, so let's get that in mind, can be transformed to a raw score where f of x equals 1 on b. This is our vertical dilation, and this is where we put it on the outside in pink. 1 over 2 root 2 pi, that's just a number, e to the negative half x minus a, so that's then represents our horizontal translation over b. And interestingly, this is our z equals x minus mu over sigma, because a is mu and b is sigma, as you can see up here and here. So therefore we get this. And this represents our function transformation from z-score to raw score, which is a little aside in a syllabus point that we need to make sure that we've covered. So we could now use integration to find the probability between two values or above or below a value for a number to exist within that continuous distribution. So let's have a look at one last example before we finish this video. And there's our normal distribution. I've got, and I'm just going to change this value again, so that's going to become a 4. I've got x is approximately equal to the normal distribution 1, 4, and that 1, 4 implies to me that mu actually equals 1 and sigma equals 2, because this is our sigma squared and this is our mu. And so on a graph, that will be, there's my mu, but because sigma is 2, it actually means that we're compressing the graph. We do a compression of 1 over b, and b is our sigma. So there's 1 over b compression, but b is our sigma as stated down here. So we're squashing the graph down half because it's 2. We're spreading it out by a factor of 2, and we've already done our vertical translation out to 1. Now, describing the translation, I've pretty much just done that. We've spread it out by a factor of 2, which is a multiplication of a half on the inside of the function. We've squashed it by a factor of 2, which is a multiplication of a half on the outside of the function. And we've shifted it to the right by 1 position because that mean has changed. And then part C is determining f of x by transforming the standard normal distribution. And so that becomes f of x equals, now I'm just going to write 1 on root 2 pi e to the negative half bracket squared, and hopefully you can see what happens here. We get a 1 on 2 multiplication, 1 on sigma times blah 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 blah, and then we get x minus mu, which is 1 over sigma, which is 2. And we might be able to simplify that. In this case, we could take that 2 out, square it, make this an 8. There's things we could do, but this is good enough. So that form is perfectly fine. And so I'd write that in summary as, probably I'd write it as 1 over 2 root 2 pi e to the, and I might just change it to 1 over 8. Taking that 2 out, squared it, it's still a part of the denominator, so 2 times 4 becomes 8, x minus 1 squared. And if you plot that function, it will be this blue one. It'll be the normal one squashed by a half, spread out, shifted up to 1. Well, I hope that made some sense. It's one of the harder things we'll do with this topic, but it's worth having that background understanding, particularly converting between Z and X scores. That's really important. All the best.